Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today we're going to talk about vector-valued functions. Okay, so we consider a particle moving through space, that is 3 space, over some time interval. And we want to ask ourselves, well, what does the path of its motion look like? Where is it at each time unit t? So the coordinates at time t, well, we get those through parametric equations, where we're going to see that each point is defined by a certain function, i.e. what I'm saying is that x is given by some function f of t, y is given by some function g of t, and z is given by some function h of t, right? Okay, so the points in space x, y, z, which gives us the points f of t, g of t, h of t, well, they make up a space curve that is the particle's path. So at each point along the particle's path, that's some point x, y, z, and those points are given by these functions f, g, and h. Okay? So for example, there's 3 space, there's x, y, z. Suppose our particle's path looks something like that, right? Get this a little closer to the line there. Well, that's falling apart, isn't it? There we go. Like that, right? So there's some particle's path. This is a space curve. And notice I've drawn it to indicate it loops over itself. This is crossing over in front. This is crossing over beneath the y-axis. Okay, so there's a sample space curve. This would be how some particle's path would look. All right, so we can also represent the space curve in terms of vectors. Since we've done all this work with vectors so far, let's apply what we know and do that. So can also represent space curve in terms of vectors, all right? And in the following sense, well, let me draw the picture first, and then we'll see what we're talking about here. So there's x, y, and z again. And we'll call the origin point O. So there's point O. We'll even use red for our space curve to set it off here. So there's our space curve. All right, and then take some point P on the curve. There's point P on the curve. Well, we can draw a vector from O to P, and we'll call it vector R, and we can do this for any point P on the space curve, right? So R of t, well, that's vector OP, right? What are the vector components of this? Well, remember, at the point x, y, z, determined by f of t and g of t and h of t, so we have just f of t is the I component, g of t is the j component, h of t is the k component, just like such, right? So we've just now translated these over to be the components of a vector. Nothing fancy going on here. Okay, so what is r of t? R of t is the vector from the origin to point P, which is given by f of t, g of t, h of t, right, at time t. Right? Keep in mind t in the background here. Each value of t determines a unique value of these functions, determines a unique point on the space curve. So that sort of longer definition, well, all that tells us is r of t is the position vector at time t. That's all this is saying here because it gives us the position on the space curve at time t. Okay? All right. So what do we call r of t? Well, if we take a look at the way it's structured, it's in terms of one independent variable, which is t, right? Three different functions based off of it, but it's now a vector-valued function. So we call r of t is a vector function or a vector-valued function. So it's a vector function, right? And what does that mean? Well, for each t in the domain, r of t assigns a unique vector to t, right? So just like a regular function, a function we think of in two variables, for every value of t in the time domain, r of t assigns a unique vector to that value t. Okay? And it should come as no surprise, f and g and t, well, those are the components of the vector that we care about. So they're called the component functions, right? And they are entirely analogous to the vector components of a usual vector we think about. And so there you go. Okay, let's see how one of these things looks as an actual graph. Now what gets very difficult is to draw an arbitrary vector function, because generally drawing space curves is not at all an easy process, but certain ones that we know a lot about, drawing is not so bad. So let's sketch the following vector-valued function. R of t is, f of t will be defined as cosine t. G of t will be defined as sine t. And h of t will be defined as just t. Okay. So before we ask ourselves, what does this thing look like in 3 space, remember, what's sometimes the best idea is to look at things that we know about, which are the xy plane. So look at a curve in the xy plane and ask yourself, how does it translate over to 3 space? All right, so let's look at that first. Well, the x and y functions, so in the xy plane, what is this thing? Well, the curve forms circular cross sections for the following reason. Well, remember, if you remember one thing about trigonometry, it's probably this equation, cosine squared plus sine squared is equal to 1. Well, cosine is the x value, sine is the y value, so this is just like saying x squared plus y squared equals 1. Well, remember, x squared plus y squared equals 1. It's a circle of radius 1 in the xy plane, right? So this thing is going to form circular cross sections. All right, well, then what happens to it here? Well, this value of t, as long as we let t range throughout negative infinity to positive infinity, these circular cross sections just go up and down infinitely far, right? So the curve, the whole curve we care about, lies on a circular cylinder of radius 1 that goes infinitely far up and down. So notice what I'm saying here is we're not drawing a circular cylinder here and calling that our vector valued function. No. A vector valued function is a curve in space, but that curve will wrap itself entirely around a cylinder. So if we draw the cylinder, we can see how the curve will at least adhere to it. So what I'm saying is the following. Let's come over here. So there's x, y, and z. X, y, and z. And so let's see, down here in the xy plane, we have a circular cross-section like that, and extends up. And it would extend down also, but I'm not going to draw that. Here, let's make this go a little taller. So that looks like that. This should be dashed like that, and then I guess that this should be dashed also to indicate that it's at the base of the cylinder. So there's the circular cylinder. This radius here from the center point, this is 1, right? Our space curve is going to lie on the outside of this cylinder entirely. It's going to wrap itself around the cylinder, okay? So this is the upper half of the circular cylinder, right? And the entire curve lies on the outside of this, right? And remember, this would also go infinitely far down below and infinitely far up, right? Okay? And think about it like this. Well, wherever the curve starts in the xy plane, right, cosine and sine are both periodic functions. They repeat every 2 pi intervals. So as my t values repeat every 2 pi intervals, the curve will also repeat every 2 pi intervals. So this thing will keep rising, but it's going to keep coming back around to the same spot in the xy plane every time we go 2 pi in the time interval, right? So what I'm saying there is as t goes from 0 to 2 pi, the curve makes one complete revolution around the cylinder. So as t goes from 0 to 2 pi, and again from 2 pi to 4 pi, and from negative 2 pi to 0, and so on and so forth, the curve will make one complete revolution around the cylinder. Okay? All right, so what do we have then? Well, think about it like this. So let's draw our x, y, and z. So there's x, y, and z. So when t is 0, right, remember our curve was, I'll put it up here again, it was cos ti plus sine tj plus tk. Well, when t is 0, cosine of 0 is 1, sine of 0 is 0. This piece is 0. So we're starting off down here at 1, 0, 0, right? So this is when t equals 0, like that, right? And then when t is 2 pi, well, cosine is again going to be 1. Sine is again going to be 0. This is going to be 2 pi, right? So up here somewhere, there's a point that's 1, 0, 2 pi. And that's when t equals 2 pi, like that, right? Because think about it like this. We're at the exact same position in the xy plane we've just gone 2 pi units higher. And what's going to happen is we're going to wind up with a helix. Let's see if we can't get this to look a little darker here. That's better. And then we're going to have something that looks like that. So can the whole thing look better? Yeah, that looks better, yeah. Wind up with a helix, and so this thing crosses in front of the y-axis there. And let's see, so, and then this part is going to pass underneath and that top part of the helix. The trick is finding the good part of the marker. There we go. That's going to pass underneath, and this is going to pass on top like that, right? So wind up with a helix, and think about it like this. So this thing is just twisting and revolving around this cylinder over and over again in a helical structure. Every 2 pi units, it comes back around to the same spot it began in the xy plane, only it's 2 pi units higher, and the helix will wrap itself around forever and ever and ever as you go up and down the cylinder. Okay? All right, so that looks good. Okay, now like I said, that's a space curve we know a lot about. Helices are pretty easy to draw. Lots of space curves, well, much harder to draw, so we're going to leave it at that for the time being. All right, let's shift gears a minute and talk about limits and continuity of these things, because if we're going to work with vector-valued functions, we want to be able to do calculus on them. So we've got to know about the operations which are fundamental to calculus: limits, continuity, derivatives, integrals. And fortunately for us, not a whole lot is different here from the 2-variable case. So limits and continuity, and the subsequent discussion here is going to be very familiar to us from our talk about limits and continuity of single variable calculus. So we have some vector-valued function, f of ti, g of tj, h of tk, right? Well, what's our limit going to look like? Our limit definition, the limit as t goes to t naught of r of t, well, should come as not a great surprise to us that limits are just done component-wise, right? In other words, the limit definition extends entirely to each component just as we would expect it to. So the limit as t goes to t naught of g of t, that's the j component, and the limit as t goes to t naught h of t, and that is the k component. So here, our limit as t goes to t naught of r of t is just done component-wise as such. So limits are done component-wise, and it's not going to be much of a surprise to us that basically everything else we're going to do with vector-valued functions, other operations, are also done component-wise also, which is nice. Okay, and continuity has an analogous definition, so I'm not going to present any kind of the epsilon delta definition here for either one of these, but r of t continuous at a point t equals t naught, excuse me, if and only if each component function is continuous at t equals t naught. So there's no reason to reinvent the wheel here and go through all the definition of continuity and limits from single variable calculus. It doesn't matter. We know what those are. What we also know is that those definitions carry over analogously to vector-valued functions. So continuity happens only if each component function continues at a certain point. Okay? All right, so an example. Let's get rid of this. All right, so this should be very little surprise in this example. So let's find the limit as t goes to pi over 2 of r of t if, let's see, let's use something that's close to a helix here, which is cosine 3t I plus, or at least close to a helix in equation, sine t minus 1j plus 2t k. That's a 2. Yeah. So there's the function. I want to find this particular limit. Okay. So let's see here. So the limit as t goes to pi over 2 of r of t, well, it's the limit of each component separately. So I'll write that out. Limit t goes to pi over 2 of cosine 3t. That's the ith component. The limit as t goes to pi over 2 of sine t minus 1. That's the jth component. And the limit as t goes to pi over 2 of 2t. That's the kth component. All right? Okay, so these limits are all pretty standard. These are all continuous functions at this point. There's no problems. So you plug in here, cosine of 3 pi over 2 is 0. Right, so this is 0i. And let's see, the limit, so sine of pi over 2 is 1. 1 minus 1 is also 0, so that's 0j. And 2 times pi over 2 is pi. Yeah, that's right. And so that gives you plus pi k. So your limit's going to be equal to just pi k. All right? Okay? So still a vector. All right? And notice, too, r of t is continuous on all of r. Remember, that symbol meant all real numbers. Since each component is continuous on all of r. Okay, so you had the limit, you had continuity at every point in r. We're good to go. Okay, so that's limits and continuity. They work component-wise, great. Well, derivatives work exactly the same way. Derivatives are also done component-wise, and even geometrically, they are defined in an analogous manner to what we're used to seeing a derivative defined as. Okay. So, derivatives. So again, we have our usual vector-valued function, which I'll just put up here for the sake of having completeness. So we're used to that, f of t I, g of t j, h of t k. All right, so the derivative r prime of t, which is dr dt as such, well, it's done component-wise, so it's just df dt is the I component, dg dt is the j component, and dh dt is the k component. Right? So again, this is done component-wise. All right. Excuse me. So r of t, remember, it's a position vector. It's a position vector. So let me draw a picture up here. Let's switch back to black and give some contrast. Maybe this has had time to revitalize itself. So like that. All right. So remember, so let's draw some space curve. Oh, I don't know. Like that, right? there's a space curve. Pick some point P. There's a point P. There's the vector r of t. There's the origin, right? So this is the position vector to point P on the space curve, right? Well, remember that the derivative was just the tangent to the curve in 2 space. Well, here it's just the tangent vector, right? So r prime of t is the velocity vector tangent to the curve at, well, I don't need to say at time t, but it's at time t certainly. So r prime is something that looks maybe like that, right? Right. So that's the velocity vector tangent to the curve and in the direction of the curve at time t. Okay? And it's important to make note, too, that in a lot of text, or at least in the Thomas text, r prime is often referred to as v of t for velocity. So I will use these interchangeably. In fact, probably mostly I will use v of t from this point on. However, they do mean the same thing. Okay? All right. One other thing to note, too. So remember that velocity is a directed distance to us in vector terms. So speed, remember, is just the magnitude of r prime of t, i.e. speed equals the length of v of t, right? So r prime of t is a vector. It has a direction and a length. The length of it is speed, right? So you're traveling at 40 miles an hour going northeast. Well, 40 miles an hour is the speed. Northeast is the part of the direction. So, okay. And it's worth noting, too, that just like in the 2-variable case, this is important to us later on, acceleration is the derivative of velocity. Remember that? So that is to say that when I use this a of t vector, it's dv dt, or it's d squared r over dt squared. So it's velocity's derivative, or it is the second derivative of position, just like it is in the 2-variable. Okay, so an example of this. Take a look at what's going on here. All right, so let's get rid of this. And we're going to work again on a helix, because helices, they understood very well. They're easy to see what's going on with them. All right. So let's flip back to the black here. All right. So car travels upward in a helical parking structure. Right, so you've all seen before, these helices. Let's see here. So the position at time t is what? So r of t, it's the function 2 cosine ti plus 2 sine tj plus 10t over pi k, right? So this is a helix, all right? And let's restrict t between 0 and 6 pi, because the thing is only so large, right? So it's going to make 3 full revolutions around this thing. Right away we can tell, because 6 pi is 3 times 2 pi away from the starting point, okay? All right, well, the velocity vector, velocity v of t, well, derivatives. We can do these derivatives pretty easily. This is dr dt. So derivative of 2 cosine t is negative 2 sine t I, right? And derivative of 2 sine t is 2 cosine t, 2 cosine t, j. And derivative of 10t over pi is 10 over pi k. Now what I've got here, make sure everything looks good. Yep, looks good here. Okay. And the speed, well, the speed is the length of that vector. And we'll see now that something nice happens with a helix with the speed. So we got negative 2 sine t squared plus 2 cosine t squared plus 10 over pi squared. The whole thing had the square root. So, all right, well, what's going to happen here? We're going to wind up with a 4, well, I've got to put the root around everything, so there's the root, a 4 sine squared t plus a 4 cosine squared t plus what, 100 over pi squared? Well, think about it. We can factor a 4 out of these terms, right? And so we're left with the expression 4 times sine squared plus cosine squared, right? Well, that's 1. That's 1, so let's see. So this is going to end up being what? 4 times sine squared t plus cosine squared t plus this 100 over pi squared junk. Well, that's 1, yeah. And so this ends up being the square root of 4 plus 100 over pi squared. Well, that's what? Square root of 4 pi squared plus 100 over pi squared, if I put it in a common denominator, right? But I don't care what this is. I mean, this is something nasty. It doesn't matter. The point is, though, it's constant, right? It's a constant. There's no t term in there. The speed doesn't depend on the time, all right? So the big result here, therefore, car is traveling at a constant speed, right? Well, it may be turning a lot, but it's traveling at a constant speed. It's constantly turning because it's in a circle moving in the helical parking structure, but it's traveling at a constant speed, okay? All right, well, let's look at the acceleration vector. So here's the velocity stuff, all right? That's all well and good. Let's look at acceleration. So what don't I want to erase? I don't want to erase the function itself, okay? So acceleration is a of t, and that is dv dt d squared r over dt squared. And well, I just erased v, but you have it in your, you can go back and look at it again. It's in the notes too. So the derivative of t, let's see, this was negative 2 sine t, so this would be negative 2 cosine t. This derivative was 2 cosine t, so that would be minus 2 sine t. Right? And this piece would go away because it would be 2 derivatives. That would make it 0. So there should be an I and a J in there too, shouldn't there? I minus 2 sine t j, right? Okay, so notice the acceleration vector is only in 2 space, and it's a circle. That's interesting. Also, we'll get back to that in a minute. Notice something else. So notice that the velocity vector has a constant length, right? We just said that. It's over there. It's traveling at a constant speed. So e.g. is constant. Well, what that does actually, and this is kind of an off-the-cuff way to put this, but it's an important remark, is it gives us something useful. So this applies to any vector with a constant speed, not just v, but v happens to work for us here. So the following is true. Let's take a look. Let's go over here. Let's take a look at what happens when we do v dot a. So what happens when a vector with constant length is dotted with its derivative? It's interesting. All right. Let's see here. So we get what? So v was negative 2 sine t, and a had negative 2 cosine t. So I'm just doing dot product here. Nothing fancy going on. And let's see. V's j component was 2 cosine t. And a j component was negative 2 sine t. 2 sine t, right? And so look at this. So this is what, 4 sine cosine, and this is negative 4 sine cosine. Well, hey, that's 0, right? That's 0. So these two vectors are orthogonal to each other, right? So this fact is true of any vector of constant length. And that may seem like not that useful to us now, but it's going to come in handy later on. It's going to help us understand more about 3D motion. But it's true of any vector of constant length. So let, I don't know, P of t be a vector where the length of P of t is c, right? So that vector length is c. Then the following fact is true. P of t dot dp dt is 0 for all t, right? So for all t, this is the case. P of t is a vector of constant length for all t, right? I should set for all t up here. Okay, so that fact is true. All right, and let's see, what else I want to say about this here. So we have our velocity vector, we have our acceleration vector, and notice, even though we're traveling at a constant speed, we are accelerating constantly in a circle in the xy plane, so we're constantly moving in a circular direction with our acceleration vector, right? It's constantly tangent to our vector v. All right, so let's see here, what I want to erase. Let's get rid of acceleration here. I want to draw the picture for a minute. So at time t equals 0, the car starts at position, well, plug in 0 here, you get 2, 0, and 0, so you're starting at some position 2, 0, 0. And after one complete revolution, i.e. t equals 2 pi, where is the car at? Well, this is still 2, this is still 0. This is now, 20 pi over pi, which is 20. So you're at 2, 0, 20, right? So you're moving like this, and something like that, right? And let me actually scoot this further. So there's your starting point, 2, 0, 0, and that's t equals 0. And then up here maybe is 2, 0, 20, and your time is 2 pi. And so maybe each deck of the parking structure is maybe 20 feet high, for example, something like that. So you're starting off when you come in down here, the first deck of the structure up here maybe is 20 feet high, okay? All right, so there's your differentiation. The important fact coming out of this is this fact over here that we talked about, that if you have something of constant length, then you can dot it with the derivative and it'll get 0. We'll see that again. Okay, the differentiation rules, well, they are, as expected, not much different than the regular differentiation rules. The only one that's a little bit different is the cross product rule, which just like the cross product itself, takes into account the order of the vectors involved. All right? So let's see here. So let's give orange a try and see if that's had time to warm itself up. So, yeah. Differentiation rules. All right? So a lot of these look very familiar to you. So we take d dt of what? You multiply out front. So you have some vector valued function u of t. Multiply out front by f of t. Well, then we just get the product rule plus f of t u prime of t, right? So this is just product rule. That's all this is. So this is product rule. Remember, that's what we do when we have the product of two functions. Okay? All right, what about the dot product rule? Well, dot product, remember, dot product is the operation of vector multiplication most like regular multiplication that we're used to, so it should look most like the product rule, and it does. So you have two vectors, you dot them, and you get what? U prime v of t plus u of t v prime of t. So this is the dot product rule. And notice it's basically just product rule. Just product rule, right? That's all this is. So this works just like the product rule works. Okay? The chain rule is totally analogous. d dt of what I want to say here. So you got u, and you compose it with some f of t. I guess I should use brackets out here. Well, no. Well, there we go. And you get what? Nope, that's not what I want to write. You get f prime of t times u prime. Oops, that should be an f. F of t. That looks better. Is that what I have here? Yeah. Good. Parentheses all done. Yeah. So this is just chain rule. And then, of course, you have to proceed to use product rule from here on this kind of function, right? And then, let's see here. So you've got, and then we have cross product rule. This is the one that's sort of new to us. So you have u of t cross v of t. Remember, the order matters for cross product. Otherwise, the vector changes. The normal vector changes from pointing out to pointing down or vice versa. So this is u prime of t cross v of t plus u of t cross v prime of t. Actually, up here I should have said this is the chain rule up here. So that's chain rule. And this is cross product rule. Right? And remember, order matters here. Order matters. Right? So those are the important rules. Other rules that we're used to follow suit, addition rule, things like that. I'm not going to put them up on the board, but they are the same. So things look pretty good here. Okay. Let's talk about the integrals then. All right, so there's differentiation rules. Derivatives work very similarly to regular differentiation in single variable calculus. And so integration, as a consequence, also works very similarly. So integrals. All right. And so I don't care if you're doing it definite or indefinite. They're both done component-wise. Well, that should come as no surprise to us. Everything else is done component-wise, so the same thing's going to happen here. So as an example, let's see here. So say you had a definite integral a to b of r of t dt, then that's the same as a to b f of ti plus g of tj plus h of tk, parentheses, parentheses, dt, right? So there's your r of t. Well, this will just be 3 separate integrals. Yes, I want to say this. A, b, f of t dt is the ith component. A, b, g of t dt is the jth component. And a, b, h of t dt is the kth component. All right? And it's the same for indefinite integrals as well. Nothing changes. All right? Let's do a couple examples, and then we'll finish up here. So, okay, there's the integration. Let's look first at just an evaluation problem, then an initial value problem. So, let's evaluate 0 to pi over 2 r of t dt, and we will work with r of t equals sine 2ti plus 3 cosine tj plus t squared k. Okay? All right. So, again, this is done component-wise. So, let's start over here. So we do this entirely component-wise. So this is the first integral is 0 to pi over 2 of sine 2t dt. That's the ith component. 0 to pi over 2 of 3 cosine t dt is the jth component. And 0 to pi over 2 t squared dt is the kth component, right? Okay, so what do we have here? So you needed to get sine 2t. So let's see here. We had to use, think about, this is a chain rule function, so we're doing integration by parts. So this would be negative 1/2 cosine 2t, right? Because let's see, so the derivative of negative cosine is sine. The 2 and negative 1/2 will cancel. That looks good. All right. And that's evaluated from 0 to pi over 2. That's your ith component. Over here, let's see here. To get 3 cosine t, we had to differentiate 3 sine t. Is that what I've got? Yes, good. So we need 3 sine t evaluated from 0 to pi over 2. That's the jth component. And over here, to get t squared, to do 1/3 t cubed, again from 0 to pi over 2. And that's the kth component. Okay, plug in pi over 2. So this is cosine of pi, which is negative 1. Times a negative 1/2 is positive 1/2. Cosine of 0 is 1, so negative 1/2. So you have positive 1/2 minus a negative 1/2, which is 1. Is that what I've got? Good, it is, yes, all right. So this should just give you I, all right? This over here, sine of pi over 2 is 1, that's 3, that's 0. So this is plus 3j. And pi over 2 to the third is pi cubed over 8 times 1/3, which is pi cubed over 24. So pi cubed over 24k. And that is, that's what I got here. So there is your definite integral. It's a vector quantity, right? So that's okay. All right, let's see here. So that was not too bad. It works the same way as any other integration does. Let's do one that's an initial value problem. So let me get rid of this. All right. And notice certainly with a definite integral, you expected to get out a single vector quantity without any t's in it, and we did. Right? So that was a single vector. All right, here we'll do initial value. So let's find an antiderivative. We'll call it, let's see here. So am I using R? I'm using big R, yeah. Big R of t when big R prime is sine ti minus cosine tj plus k. So now we're back on the helix again. Yeah, that looks right, yeah. And I want to find a particular antiderivative such that the initial condition r of 0, the initial position is 1, 1, 1 when time is 0. Okay? So how we do this, remember these problems from Calc 1 or Calc 2, well, Calc 1, I guess. So r prime of t dt, integrate that, right? FTC tells us that this is r of t plus some constant. Only this time it's just a constant vector, so for some constant vector, it should say constant, yeah, okay. All right, so let's see here. So we integrate r prime of t dt. Let's see here. So the integral of sine is negative cosine ti. The integral of negative cosine is let's see here. So sine, cosine, negative cosine. Integral of negative cosine is negative sine. Yeah, negative sine. Is that what I have here? Yeah, good. And then the integral of 1 is t, so some tk plus some constant vector there. So this is equal to r of t plus a constant vector, right? Okay. All right, so the initial condition, so r of 0, let's see, so that's equal to negative cosine of 0 is negative 1. So that's negative I. Sine of 0 is 0, so that's plus 0j. Plug in 0 here, that's a 0k. We want to add in our constant vector, so that's c1i plus c2j plus c3k. These are the components of the constant vector c, right? And that all better equal I plus j plus k, right? Well, negative 1 plus c1 better give us 1, so we've got negative 1 plus c1 I better equal I. C2j better equal j, and C3k better equal k. So implication here is that C1 is 2, C2 is 1, C3 is 1. All right, so there's our constant vector C. And our final antiderivative, so antiderivative is r of t, and let's see here. So we've got negative cosine I plus a 2i, so negative cosine t plus 2 is the ith component. Let's clear a little room here so this doesn't run into that. We've got negative sine plus 1, negative sine t plus 1 is the jth component, and t plus 1 is the kth component. Right? And let's see, that looks good. So there is the antiderivative, which will fulfill that initial requirement. And that will conclude the lecture on vector-valued functions.